For the last video in this section, I do want to talk about some applications. There are a ton of applications for exponentials and logs. So we're going to go through some of them here, and then we'll look at some more in the next section too. So let's look at the first one. Medical research indicates that the risk of having a car accident increases exponentially as the concentration of alcohol in the blood increases. Remember, exponentially means that it's increasing quite quickly. So instead of just having a linear increase where you're kind of adding the same value each time, you're actually having a multiplier increase. So you're multiplying that chance by that base, whatever it is. So you grow much faster here. The risk is modeled by this formula here. So R equals 6e to the 12.77x. X is the blood alcohol concentration, and R, given as a percent, is the risk of having a car accident. What is the blood alcohol concentration that corresponds to a 17% risk of a car accident? So let's use our formula here. So I'm looking for when R is 17. Now, typically we don't leave the R, we don't leave percents in percent form, but this one does say specifically that R is given as a percent. So in this particular formula, you would just use 17 here for the R. And now you're going to solve. Here I only have one exponent, and there's a lot of other stuff going on. So I'm going to divide out the 6 first. So I have 17 over 6 is equal to e to the 12.77x. Now I'm going to use my strategy of taking the natural log of both sides. I can't really do anything else. So I'm going to take the natural log of this side and the natural log of this side. Now what happens when we take the natural log of e, remember those pieces sort of just cancel out. You get that factor of 1. So all that's going to be left over is that exponent. And then finally, we divide both sides by 12.77. This is being multiplied, so we're going to go ahead and divide it out. So our exact value is the natural log of 17 over 6 all over 12.77. But you definitely going to use your calculator here. So try the calculator at home. You should get about 0.08. So the blood alcohol concentration of 0.08 corresponds to a 17% risk of a car accident. Now, this does say to also view it on a graph. So I'm going to stop sharing for a second. And I'm going to share with you guys Desmos, because it's always good to graph these. So I'm going to go ahead and type it in. Let's see. I'm just going to use y equals 6e to the 12.77x. And then you can see your graph here. I'm going to zoom in a little bit. Oh, maybe I zoomed in too much. Let's see. I'm going to put in my own values. I think that'll be a little bit easier for us to see everything. All right, so for our x-axis, let's go from 0. Let's go from 0 to 2. Because our answer is 0.8, so or 0.08. So let's go from 0 to 1 actually. And then for our y-axis, we're going to start at 0. And let's go up to maybe 20, because our answer was 17 there. All right, so you can see it a little bit here. If I'm trying to find that 0.8, so that's close to 0.8, right? You get 16.666. So we had that risk of about 17%. So you can see, again, we had around that 0.08 there. So I keep saying 0.8. And you're at exactly 16.66%. So a blood alcohol concentration of 0.08 is related to about a 17% risk of a car accident. Let's do a couple more examples for applications. All right, so here is that compound interest formula again. So we're going to come back and revisit it. So the formula A equals P times 1 plus R over N to the NT describes the accumulated value A of a sum of money P, the principal, after T years at annual percentage rate R compounded N times a year. So remember that P is your principal. That's your starting amount that would be in the account. R is the percentage rate that you're earning interest on that account, assuming let's talk about a savings account, we'll say. N is the number of compoundings or calculations a year. So here, if you keep reading, it's going to ask us to do it monthly. So if you're doing something monthly, you do it 12 times a year. So your N will be 12. And then your A is that final amount. So for instance, let's say I start with $1,000 in my account. Well, maybe at the end of 5 years, I now have $1,500 in my account. So the A value would be $1,500. So it's that final amount after you add all that interest back in. So we're going to start with $50,000. So that's our principal. And we want it to grow to 1 million. So we want our final amount to be $1 million. Sounds good to me. The annual rate is going to be 9%. And we do use decimal form. So you're going to move that decimal point 2 spots left. So you're going to use 0.09 in the formula. And we are compounding it monthly. So your end value here is going to be 12 because we're doing it 12 times a year, right? 12 months in a year. Here our question is, how long? So we're trying to find the time. So how many years would this actually take? Now, as a little side note, financial experts do recommend using rates between 6%, being very conservative, and 12% being optimistic for planning purposes. So when you actually are ready to start thinking about your retirement, or if you're investing in the stock market, again, you want to think of those as very long-term investments, not short-term. So typically when we plan for retirement, we're planning for 20 years, 30 years, 40 years, etc. So long-term investments. And most of the time, people do tend to make between 6% and 12% overall. 10% seems to be a pretty good average, historically speaking. But again, it really depends on the market at the time that you're ready to retire as well. So 6% is more of a conservative number. 12% would be quite optimistic. If I was planning, I'd probably maybe cut the difference maybe between 8 and 10%, like they did here. Use 9% as something that's a little bit more in the middle and maybe realistic. So I'm going to fill in my formula. And I want to solve for t here. So know that we have a true exponential equation. My variable is in the exponent this time. Whereas when we've seen this formula before, we've been solving for a. So this one's a little bit different. We have to solve with a variable in the exponent. So what you want to do is you want to clean this up. So first of all, I see that I have everything being multiplied by 50,000. So I'm going to start by dividing by 50,000 on both sides. Again, just to really start helping to clean this up a little bit here. And let's see, when we do that, I'm going to use my calculator and cheat 1 million. I get 20. And then I'm left with 1 plus, and I'm also going to do the 0.09 divided by 12 here. So I get 0.0075 to the 12t. I'm going to keep cleaning it up. So I can add these together, 1.0075 to the 12t. So at this point, I've kind of cleaned it up as much as I can. I have that exponential piece by itself because I got rid of that 50,000 on the outside. And now I need to solve. So at this point, what I'm going to do, I don't have much else I can do. I'm going to take the natural log of both sides. So remember here, I can bring that 12t out front, right? Those powers can come out front. So I have natural log of 20 is equal to 12t times the natural log of 1.0075. I want t to be by itself, so I need to divide out the 12 and also that natural log. You want to remember that when we take the natural log of a number, it's just a number. It's messy, so it looks kind of weird, but there's really nothing wrong with it. So you have the natural log of 20 over 12 times the natural log of 1.0075 as your exact answer. Now, try this on your calculator at home. You're going to plug in this. Just be really careful. This is your numerator. These two are in your denominator. So make sure either you use parentheses in your calculator or you do out in steps. And what you're going to get is about 33.4. And remember, T is always in years. So that's actually not too bad, right? If you take $50,000 and your account earns on average 9% a year, in about 33, 34 years, you'll have about $1 million in that account without adding any more money of your own. That's just with accumulated interest. So this is why with retirement accounts and with stock markets and things, most of us think of it as long-term investments. Most of us, unless we're in the financial industry, are not trading stocks every single day. We're thinking about it as a long-term investment, 30 years, 40 years, 20 years. To hopefully take a little bit of money and grow it so we have enough to retire, we'll say, and to live off of. All right, one more application. We have seen that the percentage of adult height attained by a boy who is 11 years old can be modeled by the function f of x equals 29 plus 48.8 times the log of x plus 1. X represents the boy's age from 5 to 15 years. That's where this model is relevant for. And f of x represents the percentage of his adult height. At what age, rounded to the nearest year, has the boy attained 85% of his adult height? So here's an example where we're using a common log instead of a log, natural log, like we have in the last couple of examples we're solving, where we have common logs here. And we know that f of x is going to be 85%. And this is kind of one of those, again, weird functions where we don't convert the percent over. It does say that it represents the percent of the height. So when we plug this in, we're just going to let the f of x be 85. A good rule of thumb is that if you have a single log or a single exponent piece, try to get that part alone. So what I'm going to do here is I'm going to get rid of these numbers. I want to bring that 29 over first by subtracting it. And then again, I want to get that log by itself. This is being multiplied, so I'm going to divide it out. And again, this is a good rule of thumb. If you have an exponential piece or a log piece, so here I had a single exponent in the problem, here I had a single log in the problem, try to get that by itself if you have nothing else that you can really think of doing. That's usually a good start. So I'm going to just leave this as 56 over 48.8 for now. And then I have log of x plus 1. Now, here this one's a little bit different. So normally I'm used to taking the log of both sides, but I can't really do that here. So I'm trying to think, and I'm going to use my exponential rule. So remember how I can change my log back to the exponential form? I'm going to use that here. So when you're solving these, think about the strategies that you have, right? When we're solving exponentials, we tend to take the log a lot of times. When I have a log, I try to take the exponential. We kind of try to switch it back and forth, see if that helps. Sometimes it does, sometimes it doesn't. So here I'm kind of stuck and I'm like, I don't know what to do now. So I'm going to try the exponential form. If there's no base, it is 10. So remember, this is your base and the equal side becomes your exponent. So this becomes 10 to the 56 over 48.8 power is equal to just x plus 1. Now I subtract 1 from both sides and I get 10 to the 56 over 48.8 power minus 1 is equal to x. So this is my exact answer, but it does say to round. So let's take out our calculator here. So I have 10 and I'm going to use my power key. Oops, that's not my power key. Now I would make sure that this is in parentheses. So I want to do 56 divided by 48.8, close my parentheses. I'm just letting my calculator know that this whole thing is in the exponent. And then I'm going to hit enter and then do -1. So I have about 13.05 as my answer. So this one is to round to the nearest year. So this is about 13 years old. So on average, most 13-year-old boys will have attained about 85% of their height at this point. So once they hit 13, I mean, you still have some more growing to go, but only 15% more on average. So just kind of an interesting formula here of how to kind of predict that growth spurts as well. And of course, everybody's a little bit different, right? So we're talking about overall the model that we see from the population. People can still vary individually, of course, here, but just an interesting model.